This week we are going to switch away from talking about programming like we have for the last couple weeks and move into statistics. And the first topic that we're going to touch on is a concept that is fundamental to statistics, and that is the idea of probability distributions and randomness. Now, the real conceptual leap that we have to make to understand why randomness and probability are central to statistics, or that what we have to imagine is that the observations or the data that we collect on what really happened in our system are really just one realization of the much larger set of possible outcomes that could have occurred. So there's any number of things that could have occurred in our system. Some may be very unlikely and some may be very likely to have happened. And the likelihood of any particular observation happening is governed by some underlying process that gave rise to our data. And so a probability distribution then, and that's what we'll be talking about today, describes how the values of these random variables are distributed. And we'll talk more about what random variables are in just a minute. But the key here is that since the characteristics of these theoretical probability distributions are well understood, and there's many different types of probability distributions, if we can fit a distribution to our data and then have some idea of what the underlying process was that gave rise to our data, then we can make statistical inference on the entire population to get a much better idea of what outcomes are likely and what outcomes are rare. So today we're going to cover a number of distributions and provide examples of how these can describe natural resource phenomena. And then over the rest of the course, we'll continue to reference these distributions often. So when we return to linear regression, logistic regression, and Poisson regression, we'll be talking about different types of probability distributions, giving rise to the data that we would model these with. So a random variable then is just a variable whose possible outcomes are just the outcomes of some random phenomenon. So, for example, if we roll a dice and we get a 6, we know that that number could have been something else. So if it was a 6-sided dice, it could have been anything from 1 through 6. But the fact that we got a 6 was still just a random variable because it was one random draw from that dice. So a probability distribution of a discrete random variable is just a set of probabilities associated with each of its possible values. So this is like a dice roll. And there can also be continuous random variables that we'll talk about later. If you're into gambling, you know probably a lot about random variables and their associated probabilities. Okay, so let's take a look at an example here of a random variable and a probability distribution. So let's suppose that there's some variable x that can take on values 1, 2, 3, or 4. And then we take a random draw and we want to try to predict what x is going to be. So let's say we know, in this case, that each of these values doesn't have an equal chance of occurring. So in this case, if we were to take a random draw, then in this case, it's quite unlikely, actually, that we're going to get the outcome 1 here. There's only a 10% chance of it occurring. 2 is a much more likely outcome. It has a 0.3 probability, or 30% chance of occurrence each time we take a random draw. 3 is the most likely outcome. And then 4 as an outcome is still twice as likely as 1, but not very likely to occur. Okay, so this is really just a probability distribution, and this tells us how likely each of these outcomes are to occur each time we take a random draw from this distribution. So if we were to take a random draw and we wanted to know what's the probability that x would be equal to 2 or 3, then we just add the probabilities of 2 and 3 occurring, and that would be 0.7. And then similarly, if we wanted to say, well, what's the probability that x is going to be greater than 1, or alternatively, that x is going to be not equal to 1 in this case, then we would just take 1, which is, since we've taken a draw, there's a 100% chance we're going to get an outcome, and then we subtract the probability that x is equal to 1. And so the probability of x being greater than 1 or not equal to 1, which are the same thing in this case, is 0.9. This is just review of like high school probability, but this is a good way to sort of think about a random variable, which is a draw or an occurrence, a realization of x that's coming from some underlying process here, and this would be this probability distribution. Now we can describe probability distributions in a number of different ways. So one way is to describe it using this probability density function, or sometimes it's abbreviated PDF, and that's shown right here. And so all this shows is that the probability of 1 occurring occurs the 0.1 frequency. The probability that we get the outcome 2 is 0.3, 3 is 0.4, and 4 is 0.2. 2 here. Okay, so we can see here that what are the likelihoods of each of these outcomes occurring as you move along the x-axis. We can also summarize probability distributions using what's called a cumulative distribution function. And so that's, as we move from left to right, we say, what is the probability of getting this outcome? We're looking down here now. What is the probability of getting this outcome? We move to 2, then now we're saying, what is the probability of getting 1 or 2? And then when we get to 3, it's what is the probability of getting 1, 2, or 3? And by the time we get to 4, we've exhausted our outcomes and our probability is 100%. And so this cumulative density function, or CDF, tells us, as we move from left to right, what is the probability of getting all the outcomes to the left of where we're currently at. Now there's two general types of probability distributions. They can be discrete, and that's where the probability of a discrete random variable is just a set of probabilities associated with each of its possible values. So this would be like rolling a dice. And if it's a fair die, then the probability of each of those 6 outcomes is going to be the same. And so we sometimes call this a probability function or a probability mass function for a discrete probability distribution. But it could also sometimes be continuous. So in the case of rolling a die, you can't get outcomes like 1.5 or 1.7. It has to be 1, 2, 3, 4, 5, or 6. But sometimes you should expect to get outcomes in a continuous range, and so in this case, an unbroken continuum of possible occurrences. And so if a variable can take any value in an interval, then we would consider it continuous. So this might be like your birth mass, for example, might be summarized using a continuous probability distribution. Now there's a number of different types of discrete probability distributions, again, where the outcome takes on a countable number of possible outcomes. And so we'll talk about some of these in more detail in the rest of this lecture, but we can have a discrete uniform distribution where all the outcomes are equally likely. That would be like a fair coin or a fair die. We can have a Bernoulli distribution where the outcome is either 0 or 1, and we often use this to describe survival processes. We can have a binomial distribution, and so this is where essentially just an extension of the Bernoulli process, where now we're talking about multiple individuals that are all subject to this binary outcome, like a survival process, but now we're applying this to a whole population. We can have a negative binomial distribution, which rather than counting the number of successes in a fixed number of trials, like in the binomial, this counts the number of failures before a predetermined number of successes occurs. And so this is just a different extension of the binomial distribution. And then another common distribution that we use in ecology is the Poisson distribution. And this tells us about the number of events that are occurring within a fixed time interval. And so we often use the Poisson distribution to model count data or abundance data. And there's a bunch of other ones as well, but these are really the most common ones and the ones we're going to talk about today and in the lab. So we can summarize certain properties of these distributions using mathematical equations, and we're not going to focus too much on that here, but it is good to know that you can use different mathematical equations for each of these different probability distributions to say predict what is the probability of X, which is a particular outcome, occurring under a discrete distribution or a binomial distribution or a Poisson, etc. You can calculate the expected value or the mean outcome from this distribution using particular equations, and what is the variance in different outcomes, and they'll differ between these different distributions. So let's just start by taking a look at the discrete uniform distribution. And so again, if we assume that there's a certain number of outcomes that occur with equal probability, then we would describe that using a discrete uniform distribution. And so this would be like rolling a fair dice. So we'd start off by saying, okay, well, the outcomes here then are bounded by some lower limit and upper limit, A and B. And so if it's a fair die, a 6-sided die, then the lower limit would be 1, and the upper limit would be 6, and then the outcome, X, has to be somewhere between 1 and 6. Then if we wanted to calculate, well, what's the probability of a particular outcome occurring? Since in this case we know that all the outcomes are equally likely because it's a uniform distribution, the probability is uniform as we move from left to right, then we can calculate the probability of any particular outcome happening just by dividing 1 by the upper limit minus the lower limit plus 1. So down here I have an example of that. So if we want to say, like, if we have a 6-sided die and we want to know what is the probability of rolling a 2, well, we just intuitively know that it should be 1 divided by 6. And so in this case, it would be 1 divided by the upper limit, 6, minus 1, which is the lower limit, and then we add 1 on that. And since these two cancel out, the probability of getting a 2 is 1 out of 6. Okay, the expected value, or we can also think of this as the mean. What is the mean? If we were to keep rolling the die over and over and over again, what is the expected value? We just take the upper limit, add the lower limit, and then divide that by 2. So essentially, just the midpoint between those two. And then we can calculate the variance in our outcomes using this equation here. So we might wonder when the discrete uniform distribution is actually useful for modeling natural resource phenomena, because, especially when we look out in nature, we often don't see things distributed uniformly. So especially in terms of like space use. So when we look out, often we'll see individuals clumped in sort of a random pattern where there's some individuals that are heavily clustered in some areas and heavily dispersed in others. And so the process of seed dispersal might generate like this random distribution, random spatial distribution. Or sometimes we'll see clump distributions that's really characteristic of animal herding behaviors. But there are some examples where individuals are dispersed uniformly. And so this is usually characteristic of when individuals are competing for resources or territories. And so in seabird colonies, sometimes nests will be distributed somewhat uniformly. There's also great examples in Africa of termite mounds that are actually considered hyper-uniform. And so the distance between these termite mounds is actually uncannily uniformly distributed. Now, a really common distribution that we use in ecology is called the binomial distribution. And so a special case of this is the Bernoulli process, where the outcome is either a success or a failure. So there's two possible outcomes, a 0 or a 1. This would be like flipping a coin, heads or tails, or right or wrong, or functional, defective, infected, or not infected, alive or dead. This would be a Bernoulli process. And then the binomial process is just the extension of this, where we're repeating those trials over and over. So for example, if we were to repeat this Bernoulli process, this live or dead outcome on a whole population, so for n individuals, then we would use a binomial distribution to model that. Now, in the case of a fair coin, the outcomes, heads or tails, occur with the same probability, 50%. But they don't always have to, especially in the case of survival. It may be much more likely that you're going to survive a particular year than that you'll die in a particular year. And so the probability of success, or we might say survival here, will have one probability, and then the probability of dying is going to be 1 minus the probability of surviving. Now, if we had n individuals that we were tracking and we wanted to know what is the probability that a certain number of those individuals are actually going to survive, then we could calculate it using this equation. If we had some probability of success and we want to know what is the expected number of individuals the expected number of successes, then we would calculate it just multiplying the number of trials times the probability of success. So that should make intuitive sense. If we had a fair coin and we flip it 100 times, the expected number of heads would be 100 times 0.5, and that would be 50. We can calculate the variance in our outcomes using this equation, where we take the number of trials times the probability of success and then multiply that all by the probability of failure. So here's a natural resource example of a process that might be binomially distributed, or that we might want to model using a binomial distribution. So let's imagine that we have a certain number of adult female salamanders in a pond that are going to attempt to breed. Some of them will successfully breed and others won't. But breeding or not breeding are the two possible outcomes for each female salamander. So our pond is going to be our sample unit, and then the number of females attempting to breed is going to be the trial size. Now, of the females that actually attempt to breed, some percentage of them will be successful, and the number of successful females is that outcome. So we might find that 80% of the females that attempted to breed were successful, but the underlying process was a binomial one, because for each female, they either breeded successfully or they didn't breed successfully, and there was a certain probability associated with each of those two outcomes. Now, when we scale that up to the whole population, we would get some number of successful females overall out of the total set of females that attempted to breed. Okay, the Poisson distribution is what we would typically use to model count data. And so, because counts can't be negative, there's a lower bound on count data that's 0 when we observe 0 individuals. But there might be no theoretical upper limit on these counts. And so this distinguishes it from the binomial distribution, which has some bound on either side. And it turns out that the Poisson distribution is just a one-parameter distribution, and you describe it using this symbol lambda. So the mean of a Poisson distribution is lambda, the variance of a Poisson distribution is lambda, and then depending on what lambda is, that will determine what is the probability of getting each particular outcome here. So depending on what value lambda takes on, it might be very unlikely that we get a count of 1 here, or 2, or 0. But if our distribution had a different value of lambda, it might be very likely to get these particular outcomes. And so lambda determines the overall shape of the distribution and the likelihood of our different outcomes. So here's just an example. We might model the number of individuals in each quadrat within a vegetation plot using a Poisson distribution. So here we had 46 quadrats that had no individuals in them, 36 quadrats that had 1 individual, 15 that had 2, 3 quadrats had 3 individuals, and no quadrats had more than that. Now we could substitute different numbers into our equation if we just go back one slide here for lambda until we find one that seems to fit our distribution of observed values very well. And we find that with a value of 0.75 here for lambda, that we can actually very closely approximate what we actually collected in the field. And so then using this, we could actually predict if we were to go out and sample a new quadrat, what is the likelihood then, based on this Poisson distribution, of getting each of these different outcomes. The last distribution that we'll look at quickly is the negative binomial distribution. And so this is a discrete probability distribution of the number of successes in a sequence of Bernoulli trials, so these success or failure trials, that occur before a specified number of failures. So we keep watching this success or failure process happen in trial after trial after trial after trial until we get to a specific number of successes that we're looking for. So in natural resources, this would be a good example. Let's say that we had an oil company conducting a geological survey, and we think that an exploratory oil well should have about a 20% chance of striking oil. Well, then we could ask, what is the probability that the third strike of oil comes on the 7th well that we drill? So this is where we'd use the negative binomial to figure this out. And applying this probability to the equations presented on this page, we end up with this about 5% chance of striking the third successful oil well on the 7th time we drill. The take home here from this section on discrete distributions is that we often use discrete distributions to summarize outcomes related to counting. So the number of individuals we observe in aerial surveys, or the number of successes in a certain number of trials. So examples where we would use these discrete distributions: wildlife sampling, again, abundance sampling. If we're counting the number of flowers on stems of different plants, then we might use a discrete probability distribution to summarize that. Entomology, say the number of bugs occurring on different leaves. Disease incidence, clinical trials. In genetics, the number of mutations on DNA strands. There's lots of applications of these discrete distributions that take on discrete numerical values rather than continuous ones. Now, often our data won't fall into discrete categories like count data might, and instead we might have information, say, like on individual mass that can take on really any value in a particular range. So you can have any number of decimal places. You can have individuals that weigh 3.1 grams, 3.111 grams, 3.1115 grams, and so we would use a continuous probability distribution to model this type of data. We usually say that these probability distributions have support over a particular interval. So some might have support from negative infinity to positive infinity. So this would be like normal distributions would have this type of support. Some might be supported only from 0 to positive infinity, sort of like the Poisson distribution we talked about earlier. Or some might have support across a specific interval, like from 0 to 10. We'll talk about three main ones today: the continuous uniform distribution, the normal distribution, and then eventually the exponential distribution. But there's many others that we will return to later in the course as well. And again, we can summarize some important properties of these distributions using specific equations. So we'll start off with the continuous uniform distribution. And so here, this is very similar to the discrete uniform distribution. And here we have a range of values that can occur from A all the way up to B. But any value in between here with any decimal place and any degree of precision can theoretically occur. And they occur with equal probability here. Now, probably the most common continuous probability distribution is the normal distribution. You will encounter this distribution over and over, and there are many processes in nature that generate data that's normally distributed. And in fact, many statistical techniques actually assume that your data is normally distributed. And so this one is a very good one to become very familiar with. The normal distribution is symmetric, and it's bell-shaped, so that it will have a mean that occurs right in the middle of the distribution, and values near that mean will be the most common values that occur. As you get out towards the tails on either side of this distribution, those values are less and less likely to occur. Now, theoretically, these tails reach an asymptote as you move out towards positive infinity and negative infinity, but they never really reach a zero probability of occurrence. They just get very, very, very close. And so it's theoretically possible that you could get these extreme outliers on either side of the distribution, but in reality, most of the data occurs within 2 or 3 standard deviations from the mean. So about 68% of the data from a normal distribution will occur within 1 standard deviation of the mean. About 95% of the data tends to be within 2 standard deviations of the mean, and almost 100%, 99.7% of the data from a normal distribution will be found within 3 standard deviations of the mean. So here's a look at just a few different normal distributions. And there's really 2 parameters that control the normal distribution. Every normal distribution has a mean, that's mu, this little symbol mu, and every normal distribution has a standard deviation, denoted by sigma here. So on the left side here, we have a bunch of different normal distributions that all have the same sigma, the same standard deviation. And again, this controls how dispersed the data is. But they have different values of mu, different means. And so as we change the value of the mean, the whole curve gets shifted from left to right. But since we aren't changing the standard deviation, all of these curves have about the same width. On this side of the slide, we see that all these curves have the same mean, so they're all centered on the same place, but they have different standard deviations. And so as we increase the standard deviation, the data becomes much more spread out. And what that means is that these extreme values are more likely to occur for normal distributions that have high standard deviations. So if we have a normal distribution with a very low standard deviation, like this one, then these extreme values, even say out past 2, are almost guaranteed to not crop up in your data, whereas values close to the mean, 0 here, are very, very likely to occur. Now, because the normal distribution is so important for science in general and in ecology, it probably warrants just a little bit of a history lesson. And so it turns out that this idea dates all the way back to Galileo, who noticed that errors in astronomical observations were not totally random. So small errors were much more common than large errors, and they also tended to be symmetrically distributed around a particular mean value. So then, nearly a century later, 2 researchers, and I'm going to try to bust out my Canadian heritage here and pronounce this correctly, Adrien Marie Legendre and Carl Friedrich Gauss, worked out the details of what is known as the normal distribution. And so, because Gauss worked this out, the normal distribution is sometimes referred to interchangeably as the Gaussian distribution. And so you'll sometimes hear that people say that the error in their particular model followed a Gaussian distribution. What they really mean is that it's just normally distributed. It has a particular mean and a particular variance, and it's symmetrical. Okay, the last probability distribution we'll talk about that's continuous is the exponential distribution. And so this has a single parameter, and it's usually used when making statements about the life of certain materials or waiting times. So this is sort of the continuous analog of the Poisson distribution that we talked about when we were talking about discrete probability distributions. And these exponential curves can be positive or negative depending on the value of lambda here. But we can see that these are not symmetric, so some values will be much, much more likely to occur at one end of the spectrum than the other. Classic examples of data that are exponentially distributed, so one clear example is our growth curves for populations, and the human world population is a perfect example of that, this exponential process. Radioactive decay follows this exponential process, where the amount of radioactive material remaining over time decays at a particular rate. And this actually forms the basis of radioisotope dating. Different elements decay at different exponential rates, and knowing the decay rates of those different elements allows us to backdate how long those elements have actually been decaying for since they were originally produced. Now, it turns out in R, it's actually very easy to fit probability distributions and actually simulate data from probability distributions. So every probability distribution in R has really four fundamental functions. There's a root name. For example, if we're using a normal distribution, that would be norm. If we were using a binomial distribution, this would be binom. But depending on the distribution that we have, it has a particular little root name there. And then there's four functions that we can use for each different probability distribution. So if we want to calculate the density function, or the PDF, we use dnorm if we were using a normal distribution. If it was a binomial distribution, we would use dbinom. For a probability distribution, or the cumulative density, if we want to calculate the probability or the cumulative density function, we use pnorm. We can calculate the inverse of the cumulative density function using qnorm, and then if we want to generate random data from a particular probability distribution, we use rnorm. So the probability density function really tells us about the relative likelihood of different outcomes occurring across the range of data. So in this case, we see that looking at the PDF, this black line, the probability density function, that values around 0 are very likely to occur, and as we get away from 0, they're less likely to occur. And so this actually looks like a normal curve to me. It's symmetric, it has a particular mean and a variance around that mean. Again, the cumulative density function just tells us as we move from left to right, what is the probability of obtaining an observation within the range to the left of where we currently are. And so then as we move from left to right, it just becomes more and more likely that we're going to encounter some observation over here to the left. And by the time we get out to 5, the chance of us obtaining an observation less than 5 here is almost guaranteed. It's 100%. And then the quantile is really just the inverse of this CDF. And so it tells us that for a given probability, say 50%, what is the value of that associated random variable? These are just ways to transform back from one to the other. And so R can handle many different probability distributions, all the ones we talked about today. Uniform distributions, so UNIF. If we wanted to generate random data from a uniform distribution, we would use RUNIF. There's binomial, Poisson, and all the others we talked about. And we're going to talk about these in the lab this week in some more detail and show you how you can actually look at ecologically relevant questions using these probability distributions. We'll also talk about different probability distributions in upcoming weeks, but we're not going to worry about that too much today. And then eventually when we return to different types of regression, so logistic regression, Poisson regression, and survival analyses, these probability distributions become important conceptual foundations for these types of analyses. So just to sum up and review the keywords that we focused on today, we have discrete probability distributions that take on discrete values. And we talked about discrete uniform, a Bernoulli process that can take on 0 or 1, success or failure, and then a binomial process that is just a bunch of Bernoulli trials grouped together. So the survival of a whole population of individuals. Poisson is used to model count data. And we also talked about the negative binomial, which is the number of successes in a certain number of trials. We then talked about continuous distributions, so the continuous uniform, which is really just the continuous version of the discrete uniform. We talked about a normal distribution, which is fundamental to many different types of statistical analyses. And then finally, the exponential continuous distribution. We touched on the probability density function, so the probability of obtaining a particular outcome given a particular probability distribution. The expected value, so if we repeated draws from that probability distribution over and over, what is the average value that we would get? And then the variance. We talked about the cumulative density function as we move from left to right. And when we talked about the normal distribution, specifically, we talked about quantiles, so the amount of data that is found within 1, 2, or 3 standard deviations from that mean. Okay, that's it for the lecture this week and all the conceptual information I want to talk about relating to probability distributions. In the lab, we're actually going to get into some hands-on applied looks at how these distributions can be used for actual ecological data.